hello again. I'm glad you are watching all the way here. In the last one, we have said hello 3 times. And now what we want to do as the next challenge is to work with objects, understand a bit better what we've done using the world object in the first session and with the blocks and grippers in the initial intro one. So for that, I again have the simple hello world. And if we run that, we shall see just one hello world action like that. And what we want to do instead is we want to greet multiple different people. And these are neighbors. So for neighbors, we should define a type. And we will have, say, 2 neighbors in this particular problem. Derek and Maria of that neighbor. And we will want to greet hello. We want to greet Maria and say hello, Derek. And as soon as I have 2 goals like that, I need that conjunction in here. What are we complaining about? We are complaining that this is not in it. You should have stopped me. This goes to objects, objects without ducks. So please, Derek and Maria, would you move to objects? Kindly, thank you. So we started using types, so we need to declare the requirement typing, and off we go. We need to again add the n predicate and argument for the predicate and n to the hello world. And we'll change it from hello world, obviously, to just hello, because what we want in the plan is hello Derek, hello Maria. And now to make it all syntactically correct, we need to augment all the mentions of that predicate with that parameter of the action. So actually this one could have any other name here, doesn't matter. Now let's try to run that. And there we go. Now we have hello Derek, hello Maria, and oops, we are greeting both of them at the same time. Now, yes, the way to make it actually truthfully observe that we cannot speak to 2 people at the same time. We can either do the, knock it up a notch to the durative actions, or the 2 actions need to be kind of in a conflict with one another so that they couldn't be totally ordered, but they would have to be partially ordered one after the other. And perhaps a simple trick that helps us doing that is that we will couple them with a predicate that be in the effect. Nothing for readability. The colored brackets, of course, are very, very helpful here. And the predicate needs to be declared. There we go. So if we have a predicate and we set it to P at the end, that's not going to quite work. So what about not P and not P? So it's not useful for anything. Well, there we go. Now it is being, let me re-visualize that again. Yes, there we go. So we have a hello Derek and hello Maria plan that's now offset like that, just because we invented something in the model that both of these action instances are touching, and the partial ordering machinery will need to observe that they cannot both be touching it at the same time. Although, if you look closer, that dummy predicate here is pretty useless. The other usual way how you could do that without going to temporal actions is that you increase a function f, and again, for being able to do that, you better declare some initial value for f. We will again have to declare it. There it is. And in order for that to be effective, let's try just like that. That's not enough because the planner actually looks inside and sees you're just assigning some values here, increasing or whatever, but you're never using it anywhere. So let's put it into any condition or goal or constraint or anything like that, saying that f must be greater than or equal 0, which it always is, which makes it important enough. Let's re-visualize the planner, the plan. Now that's basically again signaling to the planner that the two actions are somehow communicating with one another, and they should be partially ordered like that. So that's that example. And if you had many neighbors, right? Neighbor 3, neighbor 4, neighbor 5, neighbor 6, and you want to greet them all, would you have to declare all of those predicates by name like that in the goal? That begins to be, rather verbose. So in a context of automation, then this problem file is, of course, then machine generated. Nobody spends time writing it. If you're automating some machinery, nobody should be sitting there writing problem files. So the objects typically are populated from some say database of things. The initial state gets populated from sensory data, and the goal is something that an operator selects. So if you wanted to describe this in a more general way, we actually have a way of saying for all neighbors. For all neighbors, said hello to neighbor. So with that, you can see that it goes and greets all of them nicely. And it does them in a particular order. It wouldn't quite know any difference from greeting one neighbor versus another. So each planner will take an arbitrary decision about the ordering here because it's all still the same cost of any permutation. So that's an example of using objects and types in your model, checking the total and partial ordering inside the planner and forcing it one way or another by making sure that the actions do communicate or they are locked from one another to overlap, and also a shortcut for declaring a for all condition for all neighbors. So let's see you at the next one, where we'll do something more interesting with those. See you there.